In this video, I'm going to use an example from Deeplearning4j. Rewrite the code in Java, then replicate it in KNIME Analytics Platform. The code I'm referencing is the CSV example.java code. It was written by Adam Gibson. It can be accessed using this short URL that's shown on the screen, or else you can always Google for it and look at the source code. The example uses the iris flower dataset and attempts to build a neural network to classify flower species. The dataset covers 3 species of the iris flower. More information about the iris dataset can be found on Wikipedia. The dataset is simple. Every entry has 4 features and a class label. As you can see, we label the features as x1 to x4, and then the last class label is labeled as class, and we have 3 labels, 0, 1, and 2. And this is taken from the dataset itself. This is the dataset file, iris.txt. If I open the file, you'll see that this is the first feature, this is the second, the third, and the fourth, and then this is the label. The labels are 0 for the first species, 1 for the second, and if I scroll down, you'll see 2 for the third species. I'm going to rewrite the example to implement the following steps. First, I'm going to read the data, then split the dataset into training and testing dataset, then normalize it, then build a neural network model. I'm going to build the same model that's in the example. Then I'm going to train the neural network model with the training set, and then evaluate the model with the test dataset, and then save the model to the local file system. I'll start doing that in the Java language. So let's set up the development environment. I use the NetBeans Java IDE. You can use any IDE you like. I'll start with a Maven project, a Java Maven project. I'll give it the name iris classification, and I'll save it on my desktop in a folder called Java Code, and click on Finish. Then I'm going to add some dependencies. The first dependency I need is the Deeplearning4j dependency. The core library is what I need. I'm going to choose this 0.8.0. The next dependency I need is ND4j, so I'll add that, and I'll use the version 0.8.0. The third dependency I need is DataVec, so I'll add this DataVec, also the same version, 0.8.0. And for logging purposes, I'm going to add the SLF4j, and I'm going to use the release version, not the nightly built or the alphas or everything. And just in case we needed some more functionalities, I'm going to use the simple one as a dependency as well, SLF4j simple as a dependency. And now, as you can see, we've got in the project all the dependencies available for us, and the IDE is going to download it at its own convenience while we write the code. Before writing the code, let me just set up my data file. So I'm going to copy this iris.txt, and I'm going to go in my project folder, create a resources folder, and inside the resources folder I'm going to paste the file just so that it's accessible to my code. Now that my data is ready, let's start writing the code. So I'm going to create a new class. I'll call it iris classification. Finish. Let me maximize this. So let me just set up the logger first. So I'll start with private static logger log equals logger factory dot get logger, and I'll give it the name of this class dot class, and import and I'm going to use the SLF4j logger for this case. Well, basically that's what that is in the example. I'm just copying what's in the example. Then I'll identify the location of my data file. File iris data file equals new file system.get property, and the property is user.dir or directory, user directory, plus, remember, we put it in resources and then the file name. Let me go back and show you. So it was in resources folder, and the file name is iris.txt, so iris.txt. And if you recall, in the in the steps that I'm going to implement, the last step was to save the model into the file system. So why not define my file, the model file, in the beginning of my code? So it's going to be exactly the same as this, and I'll save it in the same resources folder, but I'll call it model.bin. This is taken exactly from another example in Deeplearning4j, and I need to import the file class, and there you go. So now we are ready to write the code. In order to read the data, of course, before we read the data, let's start our public static void main string args, and then in order to read the data, there is a class called Csv Record Reader, which requires num lines to skip and delimiter. And we're going to create a new. Now, we need to specify how many lines to skip when we open the file. Let's go back to our data set, and if I open the file, the dataset file, you'll see that the first line is part of the data set. There are no headers, so we don't need to skip any lines. So we will define num lines to skip to be 0, and the delimiter is a string, and it is, since it is a comma separated, so we're going to specify the comma as a delimiter. And let me import the CSV Record Reader, and as you can see, CSV Record Reader is part of the DataVec library, of course. And we need to assign this to a variable so that we can use it later. So we will make a record reader instance of it. Now that we've created the record reader, we'll tell the record reader to go and initialize itself, giving it the file. And we're going to ask it to use the iris data file, and we're going to use the file split class to read it. And this, as you can see, says that it needs to throw an or catch an exception. So we'll do the lazy work of throwing any exception that we have, because this is just an example, not a production code. So next, we're going to do the data description for the record reader so that it can read the data for us. So we create a data record reader data set iterator. And this requires a record reader instance. It needs a batch size for handling large data sets. It needs a label index because this is supervised learning, so we need to identify in which column the labels are, and num classes as well. And we're going to create a new record record reader iterator, and we're going to because we need to use it as a reference, we're going to save the reference in iterator. Okay, data record reader, R-E-A-D-E-R, so there's a spelling mistake, R-E-A-D-E-R. Okay, right. Now, in order for the batch size, the data set has 150 rows anyway, so the code says that it's better to read the entire data in one batch size. And the labeled index. The data set, as we've seen, let me show you, the data set looks like this. It has 5 columns, and the columns are numbered 0 to 4, and we need to specify that the 4th column is the column should be used for the labeled index. So we will say int index equals to 4. Remember that it starts from 0, so the 5th column is number 4. And the num classes, remember here, the number of classes that we have, we know that the number of classes is 3 already. Next, we tell the iterator to load the entire data. And when we load the entire data, we want to save it in a variable called all data set. Oops. Let me import the data set from, yeah, that's fine. Then we want to shuffle the data, because if you recall, let me show you the data. The data is sorted where you have class 0 before class, all the data set for class 1, and all the and then followed by class 2. So we need to shuffle, so we'll say shuffle. We use the shuffle command to shuffle the data. And now the next step, let me go back to the algorithm that I was referring to. So we've read the data from the file. Now we need to split the data into 2 sets. So let's do that. So we will split the data set, and we can ask the all data to split the data set into training and testing, and we can give it a percentage, 0.65. This is exactly as in the example, and we save that in an instance of split, test, and train. Call it test and train. Split, test, and train, T-E-S-T, and train. And let's import that, T-R-A-I-N. Import that. Now that we have split our data, let's put them into 2 different variables. So data set training data is equal to test and train dot get training data, and the same way test and train dot get the test data, and we will put it in a data set called test data. We're done with splitting the data. The next step that we want to do is to normalize the data as specified in the slide. So let's go and normalize it. Now, according to the example, there is a utility class called Data Normalization. And we're going to use the normalize standardize class, and it implements the interface of data normalization. First, we need to gather the statistics of the data. So we'll say to the normalizer, gather the statistics by using the fit class, and we will give it the training data. So here we gather the, change it into different language. Okay, so gather the statistics, and then we tell the normalizer that once you've gathered the statistics, now you can transform the data set, the training data set, and the test data set. With this, we have finished the normalization of the data set. Now, next we're going to build the network model. The example builds a model that looks like this: a network that has input layer, 2 hidden layers, and 1 output layer. Of course, since the data has 4 different features in a data sample, the input layer will have 4 input nodes. Let's do that in the code. So now we're going to build the model. Let me put a log message building the model, and let's start building the model. We start with a multi-layer configuration, call it conf, and that's exactly what the example does, by the way. Equals, it starts a new neural net configuration dot builder, and we're going to build. So first, we need to specify some default values. So give it a seed of some seed value, and give it specify how many iterations that we need. So since I am going to use them, let me define them. So we can define long seed to be any number. The example uses 6, so I'm going to use 6 here as well. Iterations, the example uses 1,000 iterations, but just for fun, I'm going to change it to 1,000 iterations, and we take this and put it here. Then for any neural network, we need to identify the activation, and in the activation, we've got the DL4j has all these different activation functions. So I'm going to, the example uses the hyperbolic tan or tan-h, and after that we need to specify how to initialize the weights, and for initializing the weights we can initialize it with zeros, distribution, ReLU, whatever. The example uses the Xavier, so I'm going to use the same thing. And then we specify the learning rate, Oops. And let's choose 0.1. We don't need to put the semicolon yet. And just turn on regularization with L2. Whoops. With L2 of 1e minus 4. This is exactly as the example. Then we call list, and now we start building the layers. So we put the first layer. This is how the example does it. And the example says that we need to have a dense layer. So we need to declare a dense layer for the first part, and so it's also called a fully connected layer. FC is used as a short form for it. So let's do that in the example. So we are going to create a new dense layer, and we use the builder constructor, and the dense layer is part of this library here. And of course we need to specify that the number of input is, if you go back into the design, the number of input, we have 4 input nodes. So go back to the code and we put 4 over here, and the number of output nodes that we're looking for is 3. Let me go take you back to the design, and you'll see on this side over here we have 3. So that's what we're going to do. So you put 3 and we build this layer. This is the first layer. What about the second layer? The second layer, give it the index of 1. Again, let me go back to the design. The second layer is also, in the example, the second layer is also a dense layer that looks like this, with 3 inputs and 3 outputs. So let's do that in the code. So we got new, we're going to write new dense layer dot dense layer dot builder, and in this case the in are going to be 3 nodes and the outs are also going to be 3 nodes, and we build it. Then we need to specify, going back to the design, then we need to specify the output layer. The output layer has 3 outputs because we have 3 classes. 3 classes in the data set, and of course the output layer is always densely connected, and that is by default. So we'll add another layer, layer number 2 in this case, and this is the new, it's the output layer. So there is an output layer class, and we're going to call the builder, of course. And we can specify the loss function, and loss function, come on, search for me, loss function, we're going to use the negative, or let me first import it. Yeah, now as you can see, the loss function has, oh, you need to start with loss functions. Yeah, that's where I was going wrong. Import that, and the loss function has lots of different loss functions implemented. There you go. You got quite a few. Of course, you can use, depending on the program, depending on the problem. The example uses the negative, there you go, the negative likelihood function. And after that, we need to specify the activation strategy. And because this is classification, we can use softmax, and the number of input nodes are 3. Let me go back to the design and show you. There you go. So it's like a 3 coming into this output layer over here. and the number of out. How many output layers, how many output nodes do you need? Because we have 3 classes, we need 3 output, and we build. So this is how we build the last layer, and then we define backpropagation to be true for training and pre-train to be false. In fact, I'm just following the example exactly, and there we go. Now we have built our network. So we've covered this part over here. So we've finished with reading the data so far. Training and splitting the training and testing data. We're done with that. We've finished with the normalization, and we have done with building network. All we have to do is train it and then evaluate it. Training is very straightforward. So we run the model, i.e. train it. Let me put a log information, just following the examples. And then all we need to do is create the network and run the model. So let's create the network. So we'll use the multi-layer network. We'll call it network. New multi-layer network, and we will give it this configuration that we created. So our network is now ready. We tell it to initialize itself, and we tell the network to fit the training data. Now this is going to take some time, and I don't want to get the impression that my computer is frozen, or the program is in an endless loop or something. So one interesting utility is set listeners, where we can add new score iteration listener. Come on. New iteration listener, I believe, and for every 100 iteration we want that to, come on, what's the spelling? Score iteration, iteration listener with an N, yes. What's wrong with over here? Listener, much better. And there you go. I have to work on my spelling. So now we're done. By this step, we will be done training the network. Next is to evaluate. And evaluation is also easy. Let me just write a info evaluation. And for the evaluation, there is a utility, class called evaluation. Okay, and same spelling here. And this utility class requires you can instantiate it by itself with no parameters, or you can give it the number of classes, since we know the number of classes that we have. So we'll put 3 over here, and we want to give it the test data. So let's get the network, then the output of the network, and get the feature matrix out of it, and then tell the eval object to evaluate the test data. Of course, we get the labels. The test data needs to get the labels. Oops, I chose the wrong one. Get the labels and give it the output from the network that we just got. And we're going to print the evaluation on the screen. Now let me go back to my algorithm. So we've trained the data, we've evaluated the network, and now we want to save the model to the file system. Let's see, stats, not status. We want to save the statistics of it. All right, for saving the model, let me log info, and I'll specify. Remember, in the beginning of the code, we identified the model file or specified the model file object. So we'll just print in the log file model file to string, and there is a utility called model serializer dot, and then we use the right model, giving it the network, giving it the file dot to string. It needs a string and true, and that's it. We just print the done message, and there we go. Our whole network is ready and our code is ready for execution. Okay, then it's time to run the code, so let's do so. I'll click on the run, and Maven is going to start, scan the project. If there are any things to be downloaded, it will download. Whoops, we've got some error, and the error says file not found. Interesting. Why the file is not found? This is this one. I think I forgot an S here. Let me just double check. Okay, let's go and see. So the resources. Yes, that's right. So let's modify the code. Get rid of S. Modify the code. So I'll put an S over here and an S over here. Save, and now it should work. So let's run the code again. As I said, if there are any libraries that needs to be downloaded, it's going to download. For my case, the library has been downloaded already. There you go. The network is being trained. It's in training session. We said, remember, we said we put 10,000 iterations over here at the bottom. You can follow the iterations. Currently it's around 3,600, 3,700, and so on. And as you can see, the error rate is going down, which means that we're doing a good job in training the network. If we just wait for a while until we reach 10,000 iterations, it's going to print the score of our network. I'm going to pause over here and come back when it's done. Right, we're back. The training is done. Let me scroll up a little bit into the output window and see that our error has reduced to 0.02. Some statistics on the classification, and here's the score, and as you can see that the accuracy is 96%, precision is 96.1%, and so on. And there you go. We've seen that we were able to train a network that looks like this and finish all the steps in the algorithm mentioned that you can see on the screen using the Java language. Now next, I'm going to replicate this experiment in the KNIME Analytics software, which has integration with the Deeplearning4j library. In replicating the same example in KNIME, I'm going to do the exact same thing except for normalizing. You can do it if you want to, but I decided not to do it. But everything else is going to be the same. I'm going to follow the exact same steps. So let's do that. This is the KNIME Analytics Platform. So I'll start a new KNIME project. I'll call it Iris Classification. And the first thing I need to do is read the data. So I'm going to use the file reader component, which looks something like this. And let me click on Browse. I'll go to the desktop. I'll go to my resources and choose the file. And I see that the file is being recognized correctly, so click OK. It's configured properly, so let me execute it and let me look at the data. And this is how the data looks like. We've got 150 rows with these columns. Now let's look back at the data again. Notice that these columns have different names. Just for neatness, I would like to rename them. So I'll look for the rename column component, click link it. I'll rename the first column. I know that the first column is the first feature, the second column is the second feature, so I'll call it X2. The third column is X3, the fourth column is X4, and the fifth column is the class column, so I'll call it class. And I need this column to be a nominal value, so I'm going to change its type to a string value. Say OK. Once it's configured, I'll execute and check the data, and voila, there you go. So the columns have been renamed. Next, we need to partition. Let me go to the algorithm. As you can see, next we need to partition the data set into training set and testing set. Let's do so. I'm going to use the partition component and connect it. Double click on it, and let's do this stratified sampling with relative. And remember, in the example we use 65% for partitioning. We'll do the exact same thing here. Click on OK and run. And let me just move this a little bit up. If you look at the first partition has 97 rows. The second partition has 53 rows. But still, there is something wrong over here. Let me look at the first partition, which has 97 rows. As you can see, it all contains class 0, class 1, and class 2, and in a very ordered manner. But if you recall, in the Java code, let me show you the Java code. In the Java code, we did a shuffle for the whole data, and we need to do the same thing over here to get more accurate results or more representing results. So I'm going to add the shuffle node, and in the shuffle we can use any random seed. And now let's run and execute both of them, and let's look at the first shuffled data. And now after shuffling, we'll see that the classes or the rows have been shuffled. Look at the classes over here, and the partition data is now much more usable. That was the first one. This is the second one, much more usable for our purpose. So we're done with reading the data. Next, we want to build the neural network model, or the deep learning model. So we'll do that here. In KNIME, under the KNIME Labs folder. I have to wait until my machine decides to show me the list. There you go. It's showing me the list. Now, under the KNIME Labs, we have a group called Deep Learning. In Deep Learning, we start with a simple empty model. Okay, and then in the perceptron, we now build the new layer, or the first layer. And the first layer, let's look at the properties. How many output we need? We need 3 outputs, if you remember. Let me show you. Let me go back all the way to the network. So in this, we needed only 3 output nodes in the first layer. So that's what we've decided. Well, that's what we've specified. Let me add the change the learning rate to be 0.01. And if you recall, we used Xavier as the initializer for the weight, and we used tan hyperbolic for the activation function. Now the same thing. Let me go back to the structure. We need another layer over here. Okay, so in KNIME, we will take another dense layer, put it here, connect it together, and configure it the same way. We want 3 outputs. The learning rate is 0.01. We're using tan hyperbolic, and the initialization is done using the Xavier. And voila, our network is ready. Next, let me go to the algorithm. Next, we are going to train the dataset, train the network on the training dataset. And the way to do that is go to the Learn Supervised subcategory, and you'll find there are 2 learners here, one for classification, one for regression. What we want to do here is classification. So we'll pull the classification and feed it the network, the model that we created, and we feed it the training data. And let's look at the configuration for this node. Now in the configuration, let's look at the learning parameters, optimization algorithm, stochastic gradient descent, that's good. We can give it a random seed. Remember, we in the example it was 6, so we'll put it to 6 as well. In regularization, we put this as the regularization. In the Java example, remember in the example there was it was 1,000 steps, but we chose 10,000 iterations, so we'll do that. We'll leave the global parameters untouched. We'll go to data parameters, batch size, just put 150 over there. 1 epoch is enough. In the output layer, again, the learning rate, we put it to 0.01, and initialization is with Xavier. And the loss function, if you remember, it was negative log likelihood. And for the columns, it has already identified class to be the target column, and it has identified the 4 columns as the feature columns, so nothing to do over there. And when we're done, our network is ready for learning. Now we'll start with the execution, and while it's working, let's look at the status. And there you go. This is the current loss, and as you can see, it's reducing exactly the same way as it was doing in the Java code. I will just wait until 10,000 iterations are completed. So once they're completed, I'll come back with the recording. Okay, we're back now. The learning has finished. We've completed 10,000 iterations, and the training algorithm stopped with a loss of 0.03, which is not bad. So now what we want to do is we want to use our test data that's coming from this port of the partition and see how well did our network do. So I'm going to go into the node repository, and under the predict subcategory we have 3 predictors: classification, layer, and regression. Because this is a classification problem, so I'm going to pull the classification predictor and connect the model, the learned model, with the test data. And just double click over here. If you want, you can append the probabilities, class probabilities. It can create class probabilities for you, but for now I'm not going to do anything except the defaults as it is, and then execute. And as you can see, the prediction is much faster than learning, as expected. Now we need to score. So there is a scorer component, so I'm going to put this here and connect it and configure that I want to score between the class and the predicted class. Click OK, right mouse click, and execute with a view opening, and as you can see, this is the confusion matrix, and our accuracy is 96.22, which is pretty close to the accuracy that we got with the Java code. Let me show you the Java code, and the accuracy was, where is the output window? Output, yeah. So 96.1 that we got from the Java code, and in KNIME it's 96.2. Basically, KNIME is using the exact same engine as the Java code is using, which is Deeplearning4j. And of course, the last thing that I want to do in KNIME is save the model to the file system. This is also easy. We go back to the Deeplearning4j node repository, and in IO there is a repository called write model. I'm going to take the model, connect it to this write model, double click over here, choose the same desktop location, and I'm going to say, for example, iris model.dl4j, and save. Overwrite existing file if it exists, click OK, right mouse click and execute, and my model is saved. And I just remembered, I didn't show you the model that was saved by the Java code. And if we go and look into the output window, the model is saved in this location called model.bin. If we go to that location, iris classification resources, model.bin, that's it. It's only 1.18 kilobyte. It's a zip file, and the model is saved, that can be loaded in any other software package for execution. The model that was saved by KNIME is in this folder, and there you go, which is also quite a small model because the network is very small that we have. So there you go. In this video, although it was a little bit long one, I tried to rewrite the Java code, one of the examples in Deeplearning4j in Java, and then replicate that in the KNIME Analytics Platform.